On the screen, I have our steps for applying our integration by parts integration strategy. And I want to do a few more examples. We've done several examples so far and talked about the strategy and where it came from. But I want to do some more because the more we integrate, the better we're going to get at it. So let's do a couple more, talk about a couple more little subtle tricks or ideas that we can apply when doing integration by parts. So remember, with integration by parts, we got to pick our u and our dv, figure out our du and our v through differentiation and integration, and then we use the integration by parts formula to find it. I have my little possible strategy over here on the right side of the screen. A possible strategy for picking our u is to use that LIATE acronym, where we pick our u as the first function that appears in the integral from this list. So logs, inverse trig, algebraic, trigonometric, and exponential in that order. So in that descending order, you could also switch the logarithmic and the inverse trig. But if you have either one of those two types of functions, those are good picks to start with for your u, or any of these others as you descend in the order. And then dv is what is left in the integral after we've defined our u. Okay, let's give a few examples a try here. Let's start with the integral of the inverse sine of x dx, and this is the fifth videoed example that we're doing here. So when we're picking our, again, I'll just rewrite that acronym right here. When we're picking our u, one of the guidelines we can use is this acronym. So if we had a logarithm, we could pick that, but we don't have a logarithm, but we do have an inverse trig function. So let's let that be my u. U is the inverse sine of x, and then dv is going to be what's left over in the integral, which of course is just the dx, or 1 dx. And now we're going to use differentiation to find du. So to find du dx, the derivative of u with respect to x is 1 over the square root of 1 minus x squared. And then I would separate the differential in dx. Then I'm going to integrate over here to find v. And v, the integral of dx, is just x. So we differentiate and integrate in our process for finding our du and our v. So now what I have found is that the inverse sine of x dx is equal to, that was my u dv, that's going to be equal to, I guess I should do this in a different color, the integral of, let's get fancy. Let's do it in, like sparkly rainbow. Okay, the integral of u dv is equal to u times v minus the integral of v du. That is kind of fancy, sparkly rainbow. All right, so now we're going to take from our formula above, u times v, so we get x times the inverse sine of x. Then we're going to be subtracting v times du. So sometimes I draw my arrows in my notes, my side work over here, and that is going to be x times 1 over the square root of 1 minus x squared dx. Now we still have an integral, but our process of integration by parts is to try to get an integral that we couldn't compute into one that we can. And it turns out that I have created an integral over here that I will be able to integrate. I will have to use another integration strategy here. Let's rewrite that, x over the square root of 1 minus x squared dx. I'm going to have to use substitution. So here, let's bring that over here. My u is going to end up being, or if you prefer, we've already used, we defined u in our integration by parts. So if you don't want to reuse u in a new context, you could use w. I'm going to use u. We're used to using u, and we've finished that integration by parts piece, and now we're looking at this integral as a standalone integral. So I am going to go ahead and use u, but if that throws you off at all, just change your variable. You can use a w substitution. It doesn't have to be a u substitution. So u equals 1 minus x squared. My du then, of course, is negative 2x dx. So x dx for the substitution is going to be minus 1/2 du. We're going to get in there, make those substitutions. So we end up with 1 over u to the 1/2, and my dx is a minus 1/2 du. That minus 1/2 can come out of the integral. So we're taking the integral of u to the negative 1/2 du. And at that point, we have an integral that we can apply our basic integration strategies, power rule to, that will become a positive 1/2. And I'll be dividing by 1/2, but remember dividing by 1/2 is the same as multiplying by 2/1. So those 2's will cancel. I will have an integration constant, and my answer is the inverse sine of x plus, well, now where was my u? I did lose it up there. There it is at the top of the screen now. Plus 1 minus x squared to the 1/2, but that's the square root of 1 minus x squared plus c. And that is my integral. And in that particular problem, we actually got a chance to see, we're going to go to that problem next on the upper corner. But in that problem, we got to see a integration by parts. And then after we had used integration by parts, we used another strategy, substitution in this case, to finish it out. But the integral was, we were able to use substitution in order to calculate that integral. All right, let's take a look at another one. So again, we have to pick, if we're going to use integration by parts, I'll write that over there off to the side again, my little lie8, kind of keep that in my mind. And in this case, as I'm looking at this, it's definitely a product. So it seems like it's a good candidate for integration by parts. I don't have a log or an inverse trig, or even, for that matter, an algebraic function. But I do have a trig function. So it seems like a good starting place for my u. So u is the cosine of x. And dv then will be e to the x dx. So when I take the derivative of cosine is negative sine of x dx when I separate the differential, and when I integrate dv to get v, I integrate e to the x, which will just be e to the x. So there is my starting place. There's my u times v. Get my sparkly pen in here again, and we'll just rewrite the formula. The more we rewrite this formula, and I'm kind of being silly here with my sparkly pen, but the more we rewrite this formula, the more likely we're going to get this guy memorized. All right, so we've got our original function. I'm just going to rewrite it. The integral of e to the x cosine of x dx is going to be equal to u times v. So we get e to the x cosine of x from our work above, minus the integral of v times du. So we get minus e to the x times a negative sine of x dx. But since that's a negative sign, this will actually become a plus e to the x sine of x dx. I'm going to go ahead and write all the steps out so we have them in our video here. Okay, now we have applied integration by parts. It does not appear to be getting any easier to deal with. Notice that what we started with is an exponential times a trig function. And this integral that we have here is still an exponential times a trig function. So this is one of those cases where I'm thinking, am I going down a rabbit hole? Am I just going to be cycling? And here is a case where what we want to do is we want to actually keep going. And we want to see if this will cycle back to the original integral. Now, I don't know until I go a little bit further, so I'm going to put a little question mark there. But it looks like it might be cycling in some way, and if we can get it back to the original integral, we'll be able to use some algebra to solve. So let's take a look. I'm going to rewrite my integral. I wrote one more line here, so I'm going to rewrite this integral again, carry it down. And let's take a look. Let's take a look at this line right here. And I notice in that integral that we were just talking about that so we did integration by parts once. Let's try doing integration by parts again. So again, I'm going to go with the same pattern. We don't want to change our pattern here. We're going to still pick our u to be the trig function sine of x. We're going to pick our dv to be what's left, which is the exponential function dx. We're going to differentiate my sine of x, so I will get a cosine of x dx. We're going to integrate our exponential function e to the x. The integral of e to the x to get v is just e to the x. And then I'm going to multiply u times v and subtract the integral of v du. So let's see what that looks like. Now I am going to keep writing everything we've done so far because we don't want to lose track of where we're at. So our original integral e to the x cosine of x dx, we have found through our first integration by parts that that was e to the x cosine of x plus Now we're doing our second integration by parts. So our second integration by parts tells me that the integral of e to the x sine of x is going to be equal to, now remember, it's going to be u times v minus v du here. So that is going to be u times v from my notes right here. We're going to get e to the x times the sine of x minus the integral of v, which is e to the x cosine of x dx. And look at that. That is what we're talking about in terms of cycling back to the original. So notice that this did, yes, it did actually cycle all the way back to the original integral. That is what we started with, e to the x cosine of x. So what I can do right now is I can use a little bit of algebra. I'm going to add to both sides of this equation. This is an equation. I'm going to add the integral of e to the x cosine of x dx, and I'm going to add the integral of e to the x cosine of x. It's essentially the algebraic step of collecting like terms. The terms that I'm collecting are integrals, but I can still, if it's the same integral, I can still collect it on one side of the equation and combine those two terms. Well, each one of these, this is one integral plus another integral, so I end up with two of those. That is two integrals of e to the x cosine of x, because again, I cycled back, so I got a second one. And this was equal to, on this side, all that's left now is e to the x cosine of x plus e to the x sine of x. Now, I do have some integration constants running around here. So, plus c, plus c1, plus c2, right? I'm going to wait until the very end and just add my integration constant, because even though I have multiple integration constants I'm adding, and then right now I'm actually going to multiply both sides of this equation by 1/2 so that I can get my integral all by itself. So I would be multiplying my constant by 1/2. This becomes the integral, or this cancels, so we have solved for the integral e to the x cosine of x dx, and that is equal to, what it becomes is 1/2 e to the x cosine of x plus e to the x sine of x plus some integration constant. There was integration constants each time we integrated. We collect them all up and call them plus c, our integration constant. And that is my answer for the integral of e to the x cosine of x. So that's a nice example of an integral that cycled back to its original form and using some algebra. So here we cycled back to the original. Through repeated integration by parts. And that will periodically happen. And if it seems as if we're just kind of cycling around and not really getting anywhere in terms of simplifying our integral with integration by parts, follow it out far enough to see if you can cycle back to the original. And if so, then you can use some algebra just like I did here. Okay, let's take a look at one more example. If we had the integral of the sine of the square root of x dx, and I wanted to integrate this problem. At first glance, it's got that square root of x. So at first glance, I would actually think not of using integration by parts. I would actually think of using a u substitution. So let's use instead of u, I mentioned earlier we could use a different variable. Let's use w. Let's use w equals the square root of x, or x to the 1/2. And if that were the case, then dw would be 1/2 x to the minus 1/2 dx, or 1/2 times the square root of x dx. And I don't have that in my integral, but I do notice that x is always greater than 0, so I can manipulate this dw and dx a little bit. And if I multiplied 2 times the square root of x on both sides, I would find that dx is equal to 2 times the square root of x. Now, I do have to be careful with that because I wouldn't, I'd have to be careful of my domain issues here. I have to make sure that x is strictly greater than 0, that I'm not creating that division by 0 right there with that derivative. So here we've got 2 square root of x dw equals dx, and the square root of x itself is w. So kind of interesting little manipulations here, but we can get this entire integral in terms of w, and we won't have that square root floating around anymore. So I'll replace the square root of x with w, and I will replace dx with 2w dw. Now I do want to just simplify that a little bit, reorder the multiplication, and write it like that. So notice here now I have 2 times w, 2 times the integral of w times the sine of w dw. And now it's looking like a product that we could apply integration by parts. So I see that. So we did some substitution. We're starting to layer some of our integration strategies together here. So at the beginning, seeing that square root of x, we did some substitution, and it was a little bit of a manipulation there in the substitution to make those substitutions for that, but we've got it, and now we're going to try integration by parts to finish it out. So in this case, my u and my dv, we're going to go ahead and pick u to be w, so I keep writing this and then scrolling to the next problem. It's not written at the top anymore. We don't have any logarithms or inverse trig, but we do have an algebraic function. So A stands for algebraic. So since there's an algebraic function, there's a polynomial. It's very simple. It's just w, but that is a polynomial, so that's an algebraic function. So we'll let that be our w, and then our dv will be the sine of w dw. Now we're going to go ahead and take the derivative. So du equals dw, and we're going to integrate. So the integral of the sine of w is negative cosine of w. And then we're going to go ahead and use integration by parts, u times v minus v du. So using our integration by parts, let's see if we can keep this. We'll drop down to the next line. So this is going to be 2 times, and then my integration by parts is u times v minus the integral of v du. So just plugging into my formula for integration by parts here, u times v, we've got minus w cosine of w minus the integral of a negative cosine of w dw. And that's going to be, let's go ahead and distribute the 2 and take care of the negative. Actually, let's do two things here. That's going to become a positive. We're going to distribute the 2, so we get minus 2w cosine of w plus 2 times, and then the integral of the cosine is simply the sine, so the sine of w. We're going to integrate and distribute the 2 at the same time. Now we, of course, have an integration constant because this is an indefinite integral. And then our last step is to work our way backwards through the substitution. And so w was the square root of x. So we end up with minus 2 times the square root of x cosine of the square root of x plus 2 times the sine of the square root of x plus c. And that is my integral, where I used, again, a couple of integration strategies to get to that integral. So at first I applied substitution, and then I applied integration by parts. I do want to just say one last thing at the end of this video. I'm showing you ways to do these problems, but a lot of the problems that we work with, a lot of the integrals that we do have more than one way to do them. So, you might have done this one a little differently. You might have let your u be the whole sine of the square root of x, and you might have manipulated in that way. But anyway, there are just different ways to do it. So.